Today we're going to be talking about radicals, and the first thing we need to do is define what radicals actually mean. When we look at this, we've got this radical symbol with an A inside of it. This symbol right here is the radical sign, and we've got, that means the square root. So we've got the square root of A equals B, means that if we square B, we will get an answer of A. And it also means that B has to be greater than or equal to 0. So when we see this symbol, this radical symbol right here, that means we're talking about a positive square root. So that means B is positive or greater than or equal to 0, and it means that B squared will equal A. The principal nth root of A is defined this way. The nth root of A equals B if B to the n power equals A. If n is even, then A has to be greater than or equal to 0, and B has to be greater than or equal to 0. In other words, just like when we've talked about square roots before, you cannot take the square root of a negative number. You also can't take the fourth root of a negative, or the sixth root of a negative, or any even radical, any even index when you have a radical there. Can't do that with negatives. When we talk about properties of radicals, the first thing that we have is when you have the nth root of AB, you can break that apart. Since AB is a product, we can break that up into the nth root of A times the nth root of B. When we have the nth root of a quotient, we can again break that up, the nth root of A divided by the nth root of B. When we have two radicals, the index of the first one there is m. The index of the second one is n. And those index numbers just get multiplied together, so we end up with the product there, m times m. That's the index for our new radical of A. The nth root of A to the nth power equals A as long as n is odd. Okay, so the square root of a number squared, we have to use n being odd. So the cube root of a number cubed is just going to be that number, or the fifth root, or the seventh root. But our next property is the nth root of A to the n power is equal to the absolute value of A if n is even. Just to give you an example of this, if we take -5, for instance, and we have that squared inside of our radical, -5 squared is 25. But we know that the square root of 25 is 5. So what this rule says is that this is equal to the absolute value of -5, which is equal to 5. So that only is in effect if our index number here is even, and in this case it's a 2. So let's simplify these. We've got the cube root of x to the fifth power. What we want to do is break this up into two things, and one of them we need to be a perfect cube. So we can break this x to the fifth up into x cubed and x squared. Remember, we want to use one thing that's a perfect cube, and from the previous slide, we know that this is equal to x. This second part, we can't simplify that anymore, so we just leave that as the cube root of x squared. So our answer there is x times the cube root of x squared. For part B, we want to use things that have that are perfect fourth roots of things. So we can break this up. The fourth root of 16, the fourth root of x to the fourth, and the fourth root of y to the 12th. Well, if we think about it, what times itself? 4 times is 12. 2 times 2 times 2 times 2, or sorry, is 16. Times 2 is 16, so this becomes 2. And since this is an even index, it's the absolute value of 2. But we know that the absolute value of 2 is just 2. Okay? And actually, when there's a number here, we don't have to worry about the absolute values. It's just when there's a variable there, that's the key thing. So for this one, we've got x, and that's going to be the absolute value of x. For this one might be a little bit trickier for the y, but we can break that into y to the 4th times y to the 4th times y to the 4th. So that's going to be the absolute value of y cubed. So our final answer, we can't simplify these variables anymore. So our answer there will be 2 times the absolute value of xy cubed. With example 2 here, we want to simplify. In order to add radicals like this, you've got the square root of 18 plus the square root of 50. We have to simplify this and break them up so that we have what are called like radicals. So again, we want to break this up into perfect squares. And our perfect squares, we want to think about that. In this case, 9 is a perfect square, and it divides into 18 twice. So we can break 18 up like that. But we know that the square root of 9 is 3. We can't simplify the square root of 2, so we leave that as it is. 50 we can break up into a perfect square. 25 goes into it twice. We're still adding. The square root of 25 is 5. And again, we cannot simplify the square root of 2, so we just leave that. Now, notice that our radical parts are exactly the same. The square root of 2 and the square root of 2. That allows us to add these just like we would add like terms. So 3 plus 5 is 8 times the square root of 2. The second one, b, first of all, we have to know that b is greater than 0 so that this is even possible. We break this up into the square root of 49 times the square root of b squared times the square root of b. Well, the square root of 49 is 7. Square root of b squared is b, because we know that b is greater than 0, so we don't have to worry about the absolute value. And then we have the square root of b minus the square root of b. So notice, again, they have like radicals, the square root of b. So we have 7b minus 1. Remember, there's always a 1 in front of a radical like that. So we have 7b minus 1 times the square root of b, and that's our answer. Again, the key thing we want to pay attention to is when we break these up, we have to use perfect squares. 4, because that's 2 squared. 9 is 3 squared. 16 is 4 squared. 25 is 5 squared. And so on. We can keep going from there. 6 squared, 7 squared, 8 squared. But we have to use perfect squares when we break these up. Some more detail on these. When we have a rational exponent, a to the 1 over n power is equal to the nth root of a. That's just some notation things. This one, notice, is in exponential form. This one is in radical form. So those are the two different ways we can write that. And then more generally, for any n that's greater than 0, we can define a to the m over n power to equal this. Notice that the index is the denominator. And the number that's on the top of your fractional exponent is still the exponent. And two different ways of writing this. You can write it with the parentheses and the exponent second, or you can go ahead and write the exponent inside of the radical. If m is an even number, we have to have a being positive because, again, we cannot take the square root or the fourth root or the sixth root of a negative number. So that's going to be important as long as n is even. Okay, so convert from exponential to radical form or from radical to exponential form. So this is 16 to the 1/2 power. That means this becomes 16 to the first power inside the radical, and the index is 2. So they're really asking us for the square root of 16, and we know that that is 4. For part B, 27 to the 2/3 power. Again, this is our index, so it's the cube root of 27. And just to make our numbers easier to work with, I typically will put the 2 on the outside because we can figure out the cube root of 27 is 3. And then we've got the squared, and it's very easy to do 3 squared and get 9 for our answer. It'd be a lot more difficult to square 27 and then take the cube root of that. For part C, we have 8 to the negative 1/3 power. Let's deal with the negative first. That makes it 1 over 8 to the 1/3 power, which, using our rules now, is the cube root of 8 to the first power. And the cube root of 8 is 2. So we get our answer is 1/2. And then for part D, we have this value here. And, oh, this is in radical form, so we want to switch it to exponential. So first of all, we've got 1 over x. Remember, the index is the denominator of our exponent, so that's a 5. And then the 3 becomes the numerator of the exponent. But we don't want to leave it like that because we don't want a fraction there. So we are going to simplify this by moving it up. And just like over here, the negative moved it down to the bottom. When we move this up, it becomes x to the negative 3/5 power. And that's our answer in exponential form. To combine these expressions, write each expression with positive exponents. Remember the rule for multiplying numbers that have the same base is we add the exponents. So this will be a to the 1/4 plus 9/4, which is a to the 10/4. And to simplify that, we always reduce fractions. It's a to the 5/2 power for the first one. For the next one, similar type of idea. We've got a 2/3 plus 5/3 is 7/3 over a to the 4/3. The rule for division is that we subtract. So this is a to the 7/3 minus 4/3 power, which is a to the 3/3 power. 3 over 3 is 1, so this answer is just a. A couple more for example 4, part C. When we raise this to the 2/3 power, remember that when you have a product here, 4 times a squared times b to the 4th, that's a product. The 2/3 applies to everything inside, so it'll be 4 to the 2/3 power. Then we have a squared to the 2/3 power will give us a to the 4/3 power. And finally, b to the 4th raised to the 2/3 power. Remember, power of a power we multiply. I guess I already did that once. But it's b to the 8/3. Let's go ahead and simplify this. If we write this out, this is going to be an index of 3. We're going to have 4 squared is 16. We'll have a to the 4th and b to the 8th. So if we break that up, here we have to use perfect cubes. So we can use the cube root of 8 times the cube root of 2, the cube root of a to the 3rd times the cube root of think about it, b to the 6th is a perfect cube, and the cube root of b squared. So to finish up our answer here, we have 2, that's a perfect cube. We have a, that's a perfect cube, and this is b squared. And inside the radical, we have 2a and b squared. So that would be our answer to totally simplify that. I guess the directions only really ask us to write it with positive exponents, but this answer down here is a more correct form of the answer. So looking at part D, again, this exponent applies to everything inside there, so it'll be 3 cubed, a to the 9 halves power, b to the 3 halves power, times b to the 4th over, and I like to bring my negatives up, so let's go ahead and bring that up. So this is going to be b to the 4th, a to the positive 1/4 when we bring that up to the top. So to simplify this, 3 cubed is 27. We have, adding the exponents, 9 halves plus 1/4. We have to get a common denominator. 9 halves is 18 over 4. So that gives us a to the 19/4 power when we add that. And then a common denominator here, 4 is 8 over 2. So we are subtracting because this is division, so it'll be b to the 5 halves power. And so that's our answer written with positive exponents. 27, a to the 19/4, b to the 5 halves. Again, write these with positive exponents. Notice we can multiply 5 times 2 and get 10. This is x to the 1/2 power. This is x to the 1/5 power. And remember, when we're multiplying these numbers that have the same base, we would add them together, add the exponents. So to get a common denominator, it would be 10. 1/2 is 5/10. 1/5 is 2/10. So when we add those together, we get 10x to the 7/10 power. For part B, we've got x times the square root of x, and if we think about it, this is the cube root, that's the 1/3 power. Then if we simplify inside the parentheses, this square root of x is x to the 1/2 power. Continuing to simplify, 1 plus 1/2 is x to the 3 halves, raised to the 1/3, and then power of a power, we multiply those. 3 halves times 1/3 is x to the 3/6, which is x to the 1/2 power. So all of that actually ends up simplifying to just be the square root of x, or x to the 1/2 power. All right, rationalizing the denominator, when we want to use multiplication to eliminate any radicals in the denominator. So to simplify that, we're going to rationalize. It's called rationalizing the denominator. So when it's in this form, you just have the square root of a number. It's very simple to rationalize. We just multiply by itself. And we can do that top and bottom because, remember again, multiplying by the square root of 2 over the square root of 2 is just multiplying by 1. And that gives us 3 times the square root of 2 over the square root of 4. But the whole point in doing that is that the square root of 4 is 2. So our answer is 3 root 2 over 2. For the second one, this one's a little bit more difficult because we need a perfect 4th power. And if we just multiply by the 4th root of 3, 4th root of 3, we get the 4th root of 9. That doesn't help us because there is no perfect 4th root of 9. So what we have to understand is we actually, since this is a fourth root, we need to end up with, to make this work, we need to end up with 4 3's on the bottom. So what that gives us is the fourth root of 27 on the top and the fourth root of 81 on the bottom. And the fourth root of 81, that is a perfect fourth power. And that gives us 3 as our denominator. So again, we've gotten rid of the radical. This last one, again, it's a little bit tricky. We need a group of 3 because the index is 3. So we're going to multiply by, notice we need 2 7s. I'm just going to put them here in the same radical. How many more x's do we need to have a group of 3? We just need 1 more. So we're actually going to multiply by the cube root of 7 times x. And that gives us the cube root of 49 x over 7 times 7 times 7. Rather than multiplying that out, I know that it's 7 cubed, and this will be x cubed. So our denominator is 7x. The numerator is still the cube root of 49x. But again, when your index is 3, like this, we need a group of 3 of these. You've got 2 x's here and 1 more there. So we need a group of 3 so that it's cubed. When it's a group of 4, notice we have to have 1, 2, 3, 4 to get a perfect fourth power and be able to simplify it. Your assignment here for section P4 is on page 35. You can see the numbers there. They're also on your assignment sheet. And again, you will have tomorrow during class to ask questions and to work on some of these problems.